Let's get started. So, ladies and gentlemen, welcome to the Tech Talk of Quantum Computing by Dr. Siddhartha Bhattacharyya. It gives me immense pleasure and honor to moderate the event today in front of my respected teachers, seniors, juniors over the years. My name is Dibyendu Datta. I'm based in Frankfurt, Germany. I did my BTech in Applied Physics Department in Instrumentation. My year of entry was 1989. I have worked in various organizations like ABB, Bosch, Wipro in India as well as Germany, and currently working with Tech Mahindra. A small anecdote. I will start off with a small anecdote. In late 2019, Google was trying to solve a complex mathematical problem through conventional computers, but could not solve it. The experts at that time, in fact, calculated that by using the world's fastest supercomputer, this particular calculation will take around 10,000 years to solve it. But interestingly enough, this problem was solved in just 200 seconds by, guess what? Quantum computing. And so today we are going to talk about this particular quantum computing. This is the kind of speed quantum computing brings in, and it is proven that to process certain kinds of tasks, it is exponentially faster than classical computers. Quantum computing is not an easy subject, by the way, as it leverages the principles of quantum mechanics heavily, which itself is a very complex subject. In fact, when I was waiting in this call, one of my elders was talking about this quantum computing concept, and he was trying to determine what are the various stages of quantum mechanics, and that was his question. So I hope Dr. Bhattacharya will explain those concepts today. One of the quotes of Niels Bohr, who is the father of quantum mechanics, or at least laid down the foundation work of quantum mechanics, tells that a statement of his tells that if quantum mechanics hasn't shocked you, then you haven't understood it at all. So that's the kind of statement the father of quantum mechanics is giving. Now, some of the specific applications of where quantum computers can be very useful are where it can bring in very high speed advantage. The computing speed advantage are the areas of AI, ML, artificial intelligence, machine learning, optimization, weather forecasting, or solving problems which are currently impossible to solve through the most powerful computers available in the market. This is mostly concerned with the areas where the variables are huge in numbers, and also additionally, the variable states are also huge in numbers. So those are the situations where quantum computing helps quite a lot. I just was doing a little bit of research on this quantum computing and found that one of the areas we applied physicists can correlate. We have been working in chemical plants, refineries, petrochemicals, or power plants, and we have come across this advanced process control. And advanced process control is basically the modeling of the chemical plants or the modeling of the power plants. And this modeling actually can be done in a far easier or a better way when quantum computing is leveraged. One interesting point, or although it's on the negative side about quantum computing, is that it has the potential of actually solving the cryptographic problems. And currently, with classical computers, cryptography is considered the safest bet, but it has the potential to crack those codes. But that is also on the negative side. There are various rules and regulations governing them. So let's go to the session directly. Today, we will be having an overview about quantum computing, and who better than Dr. Siddhartha Bhattacharya to provide us. Why so? The man who has authored 5 books, he has co-edited 60 books, and also he has more than 300 research publications in various journals and conferences. He has 2 patents to his credit, and and he has been a member of number of various international conferences. Dr. Bhattacharya did his bachelor's in physics, then did bachelor's in optics and optoelectronics, then master's from Calcutta University. His year of entry in our applied physics department was 1995, and by the way, he did his master's and he was the gold medalist of our university. He completed his PhD in computer science and engineering from Jadavpur University in 2008. He also received PhD habilitation, which is the highest degree possible in various European universities, from the VSB Technical University of Ostrava, Czech Republic, in 2023. Dr. Bhattacharya is currently serving as a senior researcher in the Faculty of Electrical Engineering and Computer Science in VSB Technical University, Ostrava, in Czech. He is also serving as the scientific advisor to Algebra University College in Zagreb, Croatia. So with this, I hand over to Dr. Bhattacharya for the presentation. But before that, 2 ground rules, please. All questions will be handled after this presentation. Once this presentation is done, then we will handle all the questions. Please keep a note of them. And then I would also request all of you to please mute your microphones so that it doesn't disturb during the presentation. So thank you. Dr. Bhattacharya, it's over to you.
Thank you. Thank you very much for giving me the opportunity. First of all, I'm audible to all of you.
Yes, you are.
Yes. Thank you for giving me the opportunity to share my learning experience in this upcoming technical domain for a new computing paradigm, as it is being called. So, and also it is quite a very good feeling that we are again together after I mastered from the Department of Optics and Optoelectronics from University of Calcutta way back in 2000. But then, better late than never, I have been given an opportunity for dealing with this particular tough task before my seniors, my professors over here. And for that, I am a little bit nervous today. Anyway, let us start with the title of this topic. It is a gentle introduction to quantum computing. So now, why at all we are just dealing with this, or just we are wasting our time in hearing to this particular lecture? So you see, things have been changing over the last decade, and more so, the main cause behind this, or main reason behind this, is that conventional computing paradigms or conventional machines are nearing their limitations or saturation. That means after some time, maybe within the next 2 or 3 years, you will not be able to advance it further as far as the architecture is concerned, speed, performance, number of cores, whatever you tell, whatever be the performance metrics, all these are coming to a halt, standstill, because of the fact that you cannot go beyond a certain point while just designing these architectures on a nano scale or micro scale, whatever it is. So then, what will happen next? So people or researchers are constantly in their efforts to come up with some alternative computing paradigms, and quantum computing is one of them. It is not the only one, it is one of them. So we have been fortunate enough to be at this juncture, at this era where there is going to be transition from the classical paradigm to the quantum paradigm or any other computing paradigm as the case may be. So just before moving on, let me just have give you some idea or some insight into what actually you can do with a quantum computer. So in this particular talk is actually targeted to address the whys, the whats and the hows of quantum computing. So let us see how I can manage to deliver to my fullest extent so that at least I can arouse some interest in you. So now the first thing, take a very trivial example. What is the value of 2 plus 2? So if you go for a classical computer, in a classical computer, it is simply just adding 2 bits because classical computers operate using manipulation of bits. So if you just look at this expression, it's quite simple that you have 2 bits like this, V1, V2 and V3, V4. Then you get, use some circuitry or some adder or half adder or full adder, and then you get some output like this, where this is the carry. So for a typical example, in this case, 2 plus 2, 1, 0 plus 1, 0 will give you 1, 0, 0, 4 is equal to 4. Very simple, isn't it? But then if you just think the same problem to be solved on a quantum computer, what will it look like? In quantum computer, things are not so simple, not as straightforward as you are having in a classical computer, because the only fact is that here you are concentrating on bits. The computation is only on bits, but here you are using qubits. What are qubits? We'll be coming to that later on. But the thing is that it is somewhat different. It behaves somewhat differently from the classical bits. That is why the computation also is very similar or different. So in a quantum computer, you're adding 2 qubits. Instead of adding 2 bits now, you'll be adding 2 qubits. The same expression like this, maybe one qubit is Q1, another qubit is Q2, another is Q3, Q4. You add them up, you get a carry over here. And interestingly, in this case, in the previous case, you only get one single output, definitive output 1, 0, 0. That is 4. But here you can have either of these, several outputs may be there, maybe at least because there are 3 qubits like this, one carry qubit and another 2 qubits over here. So at least for 3 qubits, you will get 8 combinations, 8 possible solutions of the problem. So you can either have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1 in this way up to 1, 1, 1. All these are possible solutions to this particular additional problem, that is 2 plus 2. So why actually it is so? Because it's the fact that these qubits actually they do not exist like the bits as such, because bits only can exist in either 0 value or 1 value. Either you can have a off or a on at the same time. But simultaneously, you cannot have both zeros and ones together. You cannot deal with both 0 and 1 together on a classical computer. But these have been taken care of by qubits, because due to quantum mechanical principles, by the principle of superposition, qubits actually exist as a linear combination of this 0 and 1. Linear combination of 0 and 1. Say, for example, weighted by one factor, one complex number, alpha and beta in this case and beta in this case. Say, for example, it is something like this. It looks like this: alpha 0 plus beta 1. More specifically, it looks like this: alpha gate 0 plus beta gate 1. What is this gate? Gate is actually a notation which is used to represent these qubit states or qubits over there. This was gate 0 is one qubit and gate 0 is one qubit and gate 1 is another qubit. So it actually represents the entire expression alpha gate 0 plus beta gate 1 represents a qubit as such. So that means qubit. That means you see gate 0 as such by itself is a qubit. qubit state. Gate 1 is also a qubit state by itself. And if you just go for a linear combination like this, you also get another qubit. So a combination of the individual basis states, also referred to as basis states or qubit states, is also a solution, possible solution. So that is why you get a combination of all these together in this form, which is actually the final outcome. You get some outcome as alpha k 000 plus beta k 001, all possible states with some weightage factors or referred to as probability amplitudes. So that means this particular qubit state exists with a probability of alpha square. This one exists with a probability of beta square. This one with a gamma square in this way. So and 111 with a probability amplitude of mu square. With the condition that, which is also referred to as the unitarity condition, alpha square plus beta square, if you take the summation of all the probability amplitudes, you will always get 1, because for a particular event to occur, the total probability is always equal to 1. So what happened to be a very simple problem, 2 plus 2, which was solved on a classical computer quite straightforward to get 4 on a go, you are getting a multiple number of solutions together, superposed together. So what will be the outcome here? So quite obvious that this entire expression is in the qubit domain of quantum domain. So these are all qubits coupled together, superposed together. So quite obvious. If you want to appreciate this result outcome, it is quite difficult because it is in quantum domain. So what you have to do, you have to convert that to classical domain by means of what is referred to as measurement, quantum measurement. So once you do the measurement, what measurement actually does, it just takes out a value of a particular state corresponding to which that particular probability amplitude has the highest value. So out of these alpha square, beta square, gamma square, up till mu square, during measurement, when whichever is the highest value, that particular state will be the output. If mu square is the highest, has the highest value, so you will get a output as 111. So 111 in classical domain, what does it mean? Actually, it is not equal to 4. You will get some values which is different from 4. If, for example, you get this one, if for example, if epsilon becomes the largest one, so then you get the correct answer 100, which is equal to 4. But then otherwise, you will not always get the same value altogether. So what is the use? If that is so, if you are not getting the correct outcome for a particular simple addition like this, and why you are at all of us are moving like anything behind the quantum computer. So now there are several problems to this particular, there are several solutions to this particular problem. That is, first of all, you are getting several outcomes at several instances. So you see, when you measure this particular expression, say at time t, you get an outcome like this, say 101. And if you repeat the measurement after some time, it is expected that always you will get 101. If and only if the entire quantum system is not disturbed by any means. That means you do not disturb the configuration of this entire superposed state. If you can keep it undisturbed, every time you measure, you will get the same output. But if at all some external disturbances or noises or errors creep in and the system changes or evolves with time, so at different instances you will get different outcomes. Maybe at one time you will get 010, at one time you will get 000 in this way. So that means at the end of the day, you will get different outcomes at different points of time. So what is the way out to get the correct outcome? So what we do generally in practice, after measurement, you generally take in a quantum computer several measurements, repeated measurements, trying to keep the quantum system undisturbed. Then what you do, you take an average of all the measurements, and then the average value or the expectation value is the final outcome of the computation. So needless to say, these machines as such are not going to be designed or not being targeted to design to solve these simple problems like this. These machines, quantum computers, are actually specialized machines targeted to solve some problems, typical problems, which cannot be solved on classical computer in polynomial time, in a definite time. So with this background, let us move to the contents or the agenda of the lecture. First of all, we'll be just giving an idea of a real IBM quantum machine. All of us know that IBM, Google, Microsoft, they have come up with quantum computers, and they are leveraging the quantum platform to the several users all across the world through cloud. So we are using the IBM cloud like this. And then, first of all, why do you need a quantum computer? If given these different problems which we have just discussed in the previous slide, why do you need a quantum computer? Then, followed by a brief introduction, mainly the milestones, and then the difference, the detailed difference between classical bits and qubits and their behavior and their computational principles. Then some other fundamental principles of quantum computing like superposition, entanglement. Then finally moving on to the quantum gates before the quantum computer architectures. So this entire lecture divided in two parts. One is the part one, this one is the part one part, and this is the part two part. Anyway, let us move on. Let us see how we can just try to understand the concepts behind this. So a quantum computer looks like this. IBM an image taken from IBM Q, courtesy IBM Quantum. So it is a quantum computer. You see, similar to those because we are discussing the same thing with Professor R&C last day. So in those years, the previous years, you have to have a large room housing a computer with valves and all these things, and inputs are being given with punch cards, and the next day you get the output. So similar things are going on at this moment because we're not in a position to get the miniaturized form of this entire technology. And I'm quite assured that even in the next few years from now, it is not possible to have a desktop quantum computer. Even if some of you are thinking like that, to invest money to buy a new desktop quantum computer and boast your pride and prestige. Anyway, so you see, it is actually hybrid architecture. Hybrid in the sense it contains some classical part and some quantum part. Not the entire thing is quantum. So you have some classical electronics over here, wires and all these things. And then you have a quantum part where this is the region where you have this quantum core processor. So if you just move on, you can have a better picture of this. It is a better picture where you see the temperature level which is being maintained to assure or to ensure that the system functions properly. So you have temperature starting from as low as 4 Kelvin to as low as the crash-test temperature 0.14 Kelvin in the processor region. Because why this low temperature? Quite obvious, because we are dealing with some ions, some atoms at the atomic level, computation at the atomic level. So that is why you have to ensure that the temperature remains very low. And then if you just blow it up, you have this processor like this, quantum coprocessor. And within the quantum coprocessor, you have some superconducting qubits, because this is based on superconducting architecture technology. And there is coupling between qubits by resonators and all these things, and some readout lines. So you have to just read out the information, because once you process some information on a quantum computer, you have to read it out by means of some readout lines, and then further processing on a classical computer. Anyway, so you can have details on this in this particular paper in Nature Communication, published in 2015. So now, how to use a quantum computer? If you are given a quantum computer, then how to use it? First of all, I already told you, it is not a pure quantum architecture. Quite difficult to perceive a pure quantum architecture given the fact that the physics is still developing. So what you must have a conventional supercomputer, the classical part. So real world inputs are coming from the user at the application level, software data, etc. Using the main memory and program memory to compute all these things, then some cache memory may be there, and then this is a conventional part, a classical part. Then the conventional CPU doing the computations, processing the data, removing redundancies, filtering the data, all these things coming up, and then what you do, you use some classical control electronics to take this data or feed this data into the quantum machine. So before moving on to the quantum machine, you have to have some encoder over here where you are encoding the data, classical data, to quantum data. To quantum data means you are encoding the bits in the classical machine to qubits on the quantum machine. Qubits. So finally, after this encoding process, qubits are coming inside, and then they are being processed inside the quantum coprocessor by means of some interfaces and detection systems, maybe microwave, optical, magnetic, etc., depending on the technology. So this is the quantum coprocessor part. Now, once the computation has been completed, what you need to do, you have to again just go for reading it out. Classical readout electronics using some classical. So before reading out, because classical electronics cannot read qubits, so you need some sort of measurement. What we discussed just now, measurement over here, to measure out the outcome of the computation, and then you get some output, maybe depending on the probability, and then you read the information out, feed it again to the conventional CPU for further processing, and then for visualization, all these things, and back to the real world as a tangible output, which can be appreciated. So you have both a classical part over here and a quantum part over here. So you cannot have a pure quantum machine as such. As of now, there is no possibility of having a pure quantum machine, because on the whole, the human beings generally deal with classical information. So you have to have some classical part, classical interface to operate a quantum computer. Then comes why at all you need a quantum computer. So it is just, you recollect the seminal paper by Gordon Moore in 1965. It states that the number of transistors in a dense integrated circuit doubles every about 2 years, leading or rather paving the way for miniaturization and integrated circuit technology development. And based on this, it was found in 1975 the number of transistors reached an astonishing figure of 65,000. So then, looking at this, he revised Moore's law, which states the number of transistors on a microchip doubles about every 2 years. Though the cost of computers is half, quite obvious, we are going to the miniature scale. So the cost is coming down, but the number of transistors going up. But then there must be some limitations. So as per the experts, computers should reach the physical limit by 2020s, beyond which you cannot go beyond that. That means, because there are several problems like the heat dissipation, high temperature transistors, which makes it difficult to fuse more and more circuit elements on a smaller region. So that is one of the bottlenecks which is going to come up in the development of classical computers. So just for the sake of understanding, some figures have been put over here. Let me just make it larger. So you see, as per Moore's law, in 1965, the number of transistors, as per prediction, was around 46, and then if you read 2006, for Intel dual core Itanium processor, it's some mammoth figure like this. And then further in 2016, it became even larger. But then after that, what actually is happening? So with time, whatever efforts we were investing on miniaturization and just fusing more and more things over there, so there must be some limitation that the entire computing paradigm is going to take a standstill. So you see, by 2030, you cannot just go beyond that. Number of transistors are going to be saturated. You cannot go beyond that limit. The thread performance is going to be saturated. Clock frequency is saturating. Wattage is saturating. Number of cores, you cannot increase further. So based on this, so that is why people or researchers are looking for alternative computing platforms, and quantum computers may be one of the answers, not the only answer. Because when Moore's law fails, there is no further advancement, no scope of further advancement in the classical domain. So to go for something alternative, maybe quantum computing, unconventional computing, bacterial computing, some other computing, all other things are there, but then quantum computers may be one of them. That is why we are discussing it now. So now, with this background, let us see some of the milestones on the development of this quantum computing paradigm. It started years back into 1981. It was proposed. The idea was proposed by Nobel laureate Richard Feynman. He found that the classical systems cannot simulate the evolution of quantum systems, which are prevalent in the nature. So that is why he predicted that a quantum computer can exponentially outspace classical computers and can discuss or address this evolution of quantum systems. That was the start altogether. And then you see 13 years after, 1994, Peter Shor developed the first quantum algorithm, Shor's algorithm, which is a factorization algorithm. It can factorize large integers exponentially and more quickly. So that is going to pose a great havoc to the existing crypto system, what my anchor was referring to. So you see, you know the crypto systems or modern cryptography is based on the fact that you cannot factorize large integers quite easily or in polynomial time. You require several years, several trial and error methods to break the particular factors, come out with the particular factor. But then Shor's algorithm is capable of breaking factorizing larger integers very fast. So that means it is posing a threat to the modern crypto systems. Although people are also devising other algorithms, other methods to thwart of this evil. And then after 2 years, in 1996, Grover he invented a quantum database search algorithm, some algorithm which actually rests or rather depends on the parallelism of quantum computers or quantum computation principles. So it was found that it's 4 times faster than any particular and best algorithm, such algorithm at that time. 1996 and then 1998, 2 years later, the first working 2-qubit quantum computer was developed to solve the Grover's algorithm. And then you see a huge gap. Around 19 years, IBM presented the first commercially usable quantum computer. And then after that, things are moving very fast rather. In 2020, after 3 years, GWAVE announced the first commercial 5,000 plus qubit machine. Now, people every day, you will find people are claiming, or that different organizations are claiming 5,000 plus, 6,000 plus, 10,000 plus. They are increasing the number of qubits. The more you can handle, the more number of qubits you can handle, the faster you can do something, do the computation. But then at the cost of some other problems which might creep in, that means errors, noises, and all these things. And also the stability of the system will be at stake, because it is not the only fact that you can do some efficient computation with more number of qubits, but you have to also keep in mind how many error-free qubits are there, because most of the qubits will be prone to error, prone to some external noises and all these things. So that is the main thing behind that. So even if there is a hype going on the creation of more qubit machines, but then also these factors are also, so people are also working on the error mitigation or error detection techniques as well, which is beyond the scope of this present treatment. Now coming to the basic thing, that is why actually at all, or how the qubits are different from classical bits. So classical bits, already we have just touched upon this. If you take one bit, you can represent 0 and 1, but then not at the same time. That means you cannot have any particular variable, for example, having both the values at the same time. You can either have a 0 or a 1. If you want to place 0 by 1, you have to erase the value of 0 in the memory and then put 1 over there, and vice versa. But not at any point of time you can have both zeros and ones together. Similarly, with the two bits, you can have 4 numbers, but then only one of them will be available at any point of time. Only one. So it becomes quite obvious, because you have only on-off mechanism of 0 or 1. So either you have this bulb blowing out, or it is put off. You cannot have both these states together. Difficult. But then let us see vis-a-vis what actually qubits can be represented with. So qubit representation is more easily understood by this figure. It is acting as a cloud, with the intensity of blue highest over here, intensity of green highest over here. So it is being the case 0, that is 0 state, and this is the 1 state, 2 poles. Now as you move towards the equator, for example, you will see there is a mixture of both green and blue here. So mixture of both green and blue means both Kate 0 is there and Kate 1 is there. Some sort of linear combination is coming off over here. So it is a superposed state. So superposition is there. So here at all, here you will get both zeros and ones together, which is impossible in classical computers with bits. Similarly, here also you also have Kate 1, but with a very low probability. Kate 0 with the highest probability, and here also Kate 0 with a low probability. Kate 1 is the highest probability. So all along this particular sphere or cloud, you have both Kate 0 and Kate 1 with different probabilities. But at this equatorial position, you have equal values of probability, which implies that this is equal superposition. So this has been discussed over here. Basic unit is referred to as qubit, often pronounced as qubit. Coined by this term was coined by Benjamin Schumacher in 1995. They exist in either Kate 0 or Kate 1, or the superposition of the two states. So if you take 2 qubits, it is one single qubit. So if you take 2 qubits, quite obvious, you will get 4 states simultaneously. As I already discussed like this, 2 qubits, 0, 0, plus 0, 1, Kate, plus 1, 0, Kate, plus 1, 1, Kate. Then alpha, you can have alpha over here, beta over here, gamma over here, and delta over here. Probability amplitude. So you can have 4 states simultaneously together. Okay, with different probabilities. Now if you just see the scaling up, if you have n qubit system, so you'll be having how many number of states, superposed states, 2 to the power n. So that is the advantage you are gaining. That is the sort of parallelism you are gaining. So you can now manipulate 2 to the power n number of states at the same time. So now you will wonder that what is the advantage you are getting. So for example, in this case, for a 4-qubit system, you have both this one, this one, this one, and this one, 4 states simultaneously. In the system, you can manipulate on. Now you can devise some algorithm to find out which particular state is the most appropriate solution. So you have 4 options together at your disposal. But in the case of classical machines, if you start with an algorithm with one single value, it may happen that value is not appropriate. At a later time, you have to run the algorithm again in a sequential manner with a different value, and then again with another different value until and unless you get the best possible outcome. But here you have all the possible solutions at the same place, at the same time, at the same place. Now your task is to develop an algorithm which can find out which particular value among this value is the best suited one to give the best outcome. So that makes it easier. Some sort of parallel computation, some parallel search has to be done. Quite obvious, the algorithms will be different from the classical algorithms. So now, you see, already you know the IBM Q, and it is also got some platform, IBM Qiskit, where you can represent this entire thing graphically. Just hold on. I don't know why it is not working. See, this is the representation on IBM Qiskit platform. It is a 4-qubit system. There are 16 states. You see, 0, 0, 0, 0 to 1, 1, 1, 1. But with equal superposition, you see the number. This is the probability axis. So here you see the probability is same for all of them. So at any point of time, you have all these 16 states together with the same probability. This is a trivial case. Maybe you will not get all alpha, beta, gamma, delta all same. But mainly for this particular case, all the probabilities are same, equal superposition, and those can be represented on the different poles of the Q sphere or the sphere, or in the previous figure, where you will see that this is the case 0, for example, 0 state, and this is some other states are also there, like 1, 1, 1, 0 state. All these states are represented on the particular sphere. They also refer to the Q sphere in the IBM Qiskit side. Also referred to as the block sphere, and if you just convert in the photonic quantum computer, it is Poincare sphere. So anyways, that means this is the advantage you are getting, is that you can handle multiple values simultaneously, which are impossible or not possible at all in the case of classical computers. Now furthermore, on qubit representation, already you have discussed that it's represented in a Kate notation like this, already discussed, on a Hilbert space. Anyway, also can be represented as column vector, orthogonal vectors like this. Qubits Kate 0 is represented by 1, 0 vector, and Kate 1 by 1, 0, 1 vector. Whereas you can also, for the sake of understanding, Kate 0 is the ground state and Kate 1 is the excited state. Since you are dealing with the particles on the atomic level, so quite obvious, you can also represent that in ground state and excited states respectively. So now, come to the some more in-depth analysis of the superposition principle. Just hold on. Okay. So already we discussed that the linear combination of each possible solution is also a solution. So Kate0 is a solution, Kate1 is another solution, and also the combination of Kate0 and Kate1 with some probability which is alpha and beta is also a solution. So this is superposed solution is also a solution. So qubits can also exist in a linear combination of states called superposition. So you can already have discussed Kate psi, superposed state, superposed qubit is a alpha Kate0 plus beta Kate1. Alpha square is the probability of finding Kate psi in state 0, and a beta square is the probability of finding Kate psi in Kate1. So now some figurative representation of the same thing on IBM Qiskit. You see for a single qubit system Kate0 and Kate1, this is the probability. For equal superposition, you have 50% each probability of each, 50% level. And if you represent it as equal superposition, that means you have something like this, alpha Kate0 plus beta Kate1. More specifically, since it is a equal superposition, you will have, just hold on. Since it is equal superposition, alpha and beta are equal to each other, that means both are equal to 1 by root 2. 1 by root 2 Kate0 plus 1 by root 2 Kate1. So what does it actually mean? It actually means that this is alpha and this is beta, both are same, that is an equal superposition. So the qubit vector will be represented by this location somewhat in this direction. Why this is 1 by root 2 and 1 by root 2? Because we know alpha square plus beta square is equal to 1. So 1 by root 2 whole square means half, plus 1 by root 2 whole square is equal to half, is equal to always 1. So it is equal super, very simple explanation. Now come to this very interesting thought experiment due to Erwin Schrödinger. He just devised a thought experiment to explain quantum superposition. Just imagine this thing, a living cat inside a box, black box. Black box means the box is surrounded, rather closed with it is a closed box and also covered with a black cloth so that you cannot see what is going on inside. So inside the box you have a Geiger counter for the measurement or detection of radioactive decay. There is a radioactive source somewhere here, it is invisible. And with the Geiger counter over here, you have some electromechanical system which operates and just moves the hammer like this. And also there is a flask of poison over here. So 4 things are there. One is the cat is living cat, Geiger counter, this hammer is there, radioactive source is there, and Geiger counter with an electromechanical system, hammer is there, and a flask is there, flask of poison. Now you see, 2 things may happen. First of all, you do not know what is going on inside. At any point of time, if the radioactive source decays, what will happen? If the radioactive source decays, the Geiger counter will take a reading, will make a reading, and depending on that, this lever or this system will operate, and this hammer will come down and break the flask of poison. The poison will spill out, the cat will drink the poison, the cat will be dead. On the other hand, if the source does not emit radiation, because we know radioactivity is a probabilistic phenomena, if it does not emit radiation, what will happen? There will be no reading on the Geiger counter, no movement of this electromechanical system, the flask will remain intact. No poison will spill out, cat will remain alive. But until and unless you open the box, you do not know what has happened or what is happening inside. That means, since radioactivity is a probabilistic quantum phenomena, so before the box is opened and its contents are revealed, the cat have equal chances of being poisoned or spared. So equal chances of being living or being dead. But you do not know whether it is either dead or alive. So in order to ascertain that, you have to open the box first of all. Once you open the box, you can either find the cat living or the cat dead, depending on whether the radioactive source has decayed or not. So according to quantum mechanics, the cat is neither dead nor alive, but in a superposition of both the states. Once you open the box, this opening of the box means you are actually destroying this superposition. That means you are doing some measurement. So you are coming from the quantum domain to the classical domain, either binary domain, either cat alive or cat dead. So then what actually happens? The combined states collapse into one of the 2 possibilities, either living or dead. So something like this. So inside the box, the cat looks like this. Cat is in this particular state, equal superposition 1 by root 2 of living cat, equal superposition of dead cat. So once you measure it, you either get this or this. Depending on, now in this case, quite obvious, it both are same, these probabilities are same. This is about a simple case, but generally these probabilities will be different. So depending on which particular probability is higher than the other, you will get that particular outcome. So now just to look at this representation, we have already just given some snapshots on the IBM Qiskit platform. Now how it actually can be represented or can be explained. So already we know that ket psi, the basis state or qubit, is represented by superposition of ket 0 and ket 1. You can also represent that by adding some imaginary term, e to the power i5, to the beta term. You can also represent it like in this expression. Now as far you know that according to unitarity condition, alpha square plus beta square should be equal to 1. So you can just, this entire expression can be just simplified to this particular expression, cos theta by 2, ket 0 plus e to the power i5, sin theta by 2, 1. So now this phi is something of the azimuth. It is actually designating the azimuth on the sphere, and theta is some angle. So if this particular expression, or you can just, if you represent that as a vector on the block sphere, this is also referred to as a block sphere. You can represent a qubit as a unit vector with r is equal to 1, radius is equal to 1 on the block sphere. This is a ket psi, which is tilted at an angle of theta. This theta over here, theta with the ket 0. That means ket 0 axis is like this. So you have theta over here, and this is the azimuth phi over here, and this is the ket 1. So that means if you just change the theta value, for example, if you just rotate this qubit in this direction, so qubit will come in this direction, maybe due to using some quantum operations or something like that. So it will move again. If you just rotate it again, it will also again come into this. So what will happen? The theta value will go on decreasing. This theta value will go on decreasing. Now, as you move this qubit towards the K0 axis, the theta value goes on decreasing, and corresponding alpha value will go on increasing. So at this point, say if it comes over at this point, and then you make a measurement. So now at this point, alpha is greater than beta. So then what will be the outcome? We will get a 0 because it is closer to the K0 axis. On the other hand, if you just move it in this direction, quite obvious, beta will go up and alpha will go down, and you will get outcome 1. But at any point of time, if you have a superposed state like this, it is difficult to ascertain what is there inside. It is a combination of both Ket0 and Ket1. So that is why several operations like rotation operation, other operations also there, which actually helps to manipulate the qubit so that you can get the best outcome in the shortest time possible. And the purpose of the algorithms, of the quantum algorithms, is such that to devise such an algorithm which can do these manipulations in an effective manner, and so that you can get the outcome in the least time possible. That is why quantum computing is giving you better results or faster results. Another interesting feature is the entanglement. What is the entanglement? So you see, let us consider one qubit, Q1, being prepared at Rajabajar Science College. Rajabajar at Science College, another system, Q2, another qubit, Q2 also at Rajabajar Science College. You take these two qubits and let them interact with each other. Once they interact, they form what is referred to as the entangled pair, EPR. Entangled pair. What is entangled pair? Entangled pair, as if, just for the sake of understanding, as if once they interact, Q1 inherits the properties of Q2, Q2 inherits the properties of Q1. So at least as if Q1 becomes a copy of Q2 and Q2 becomes a copy of Q1. So you have an entangled pair with Q1 and Q2 together. Now what you do after this is done, so what you do, you just take one of the qubits, say for example Q1, and take it to Salt Lake campus of the university, Salt Lake campus. Salt Lake. Here you have now Q1. Maybe let us suppose that you are able to take one of the qubits further away from the original location. And then what you do in the lab at Salt Lake, you try to measure this qubit. What will happen? The interesting thing is that since this Q1 is actually a copy of Q2 and Q2 also a copy of Q1, so whatever operations we do on this, whatever operation, maybe any operation like rotation, etc., or measurement operation, the same operation will also get reflected on this. That means the Q2 will also be affected by the same operation simultaneously, because Q1 is copied over here and Q2 is also copied over here. That is why you see, if you have one qubit observed somewhere, you have another qubit affected over another place. So if you, for example, keep Q1, after measurement gives you a value 0, state 0, so automatically this will give you a value of 1, and vice versa. If, for example, it is giving you a value of 1, it will give you a value of 0. So interesting. That means why this is so? It is something which is referred to as a spooky action at a distance, as if when you are making the measurement at this place, that information is being percolated to this particular place by some means at a speed faster than the speed of light. So that information also being percolated here. So after that, this qubit Q2 also gets automatically measured and gives a particular value. So very interesting. Generally speaking, it's quite difficult to appreciate that this thing. But then I do generally give this one simple story in the classes. So let me just share with you the story once again. It will make you understand more easily. So on the whole, it is a property. Entanglement is a property that gives rise to non-local interaction among bipartite correlated states. Bipartite correlated states means entangled pairs, and non-local interaction. They are placed further apart, but then also inherit the properties of each other. So let me just present the story of Alice and Bob. Alice and Bob, these two figures you know very well from the crypto systems of cryptography. So there are the story has several events. Let us see the events one by one. Event number 1. Once upon a time, Alice and Bob lived in Australia, maybe in different hometowns. Alice was living growing up in Sydney and Bob was growing up in Brisbane. Different towns. They do not know each other. Event 2. Suddenly Bob met Alice. Maybe they have come up to study in the same university. They fell in love with each other. Event 3. Subsequently, they got married to each other. Event 4. They were living happily when Alice got pregnant. So you see there's different events occurring. First of all, this first event, then second event, they are meeting each other. They are falling in love with each other. Event 3, they got married. Now Alice is pregnant. Event 5. Unfortunately, after a few months, Bob had to shift to the United States for his job. So you see something similar to the entanglement. When Alice and Bob got married, they actually got entangled. They are entangled pairs now. Entangled pairs, out of which were taking Bob away to United States for his job, leaving Alice behind. But then just imagine this story is taking place at a time when there is no formal mode of communication between different countries, different states. That means you do not have this telecommunication, you do not have this mobile phone, no internet, no snail mail, nothing. So there is no way that Bob can communicate with Alice and Alice can communicate with Bob once Bob leaves Alice. So Bob has now gone to United States and Alice is back in Australia. But Alice is pregnant. Event 6. Days pass by. After a gap of several months, Alice gave birth to a child. So Alice gave birth to a child means Alice becomes a mother. The state of Alice has changed. So we have made a measurement on Alice. What will happen to Bob now, you see? Event 7. The moment Alice gave birth to a child, Bob becomes a father. Quite obvious. Bob becomes a father. Even if he does not know what has happened to Alice, whether Alice has delivered or not, he does not know. But then, quite obvious, when Alice becomes a mother, Bob should become a father. So now if Bob's colleagues ask him whether he is a father or not, if Bob tells that no, I am not a father, he is actually lying. Because he does not know, he has already become a father. The state of Bob has already changed to father. So you make a measurement here. When Alice gave birth to a child, Alice becomes a mother. So measurement automatically takes place on Bob. Bob becomes a father, even if there is no formal communication between Alice and Bob. See the analogy with quantum entanglement. Alice and Bob got entangled when they got married. What does entangled states? That entanglement state of one of the entangled states changes. When the state of one of the entangled states changes, the state of the other state automatically changes. So when Alice changes to a mother, Bob changes to a father. So something like this, but then obviously the things are more complex than what is being taught over here, told over here. But then for the sake of understanding, I've given this story. Then comes the quantum measurements. We have discussed the quantum qubits, what are qubits, how they are different from classical bits, what superposition principle we've discussed with the thought experiment, cat experiment, and then also discussed upon entanglement, and then finally the measurement, conversion back to the classical domain. So already you have discussed, I have already mentioned this, if you prepare a quantum system in the laboratory, the position and energy of the states are measured actually. So after measurement, it is going to collapse to one of the eigenstates as a K0 or K1 depending on the probability. Now, interestingly, I told you, if the measurement is repeated without allowing the quantum state to further evolve, that means you are not allowing the quantum state to change at all. If you change it, alpha beta values will change. That means the system will evolve. But if you allow the system to remain the same without change, successive measurements will always give you the same result. Quite obvious because the configuration is not changing. On the other hand, if the preparation is repeated, that means if you prepare the quantum system again, so you start with alpha K0, beta K1, say for a superposed state, and then and you go for measurement, you get some outcome, and then after some time you go for another, you just prepare the system again. So in that case, maybe you can get alpha 2 K0 because these are random probabilities and beta 2. So quite obvious that alpha is not equal to alpha 2. And beta is also not equal to beta 2. So that is why every time you change the system or the system is changed or you repeat the preparation, subsequent measurements are going to give you different results. Then what is the way out? Because you are getting different measurements at different times, at different place. So you go for what is referred to as the average or expectation value of the measurement. That is the final outcome you are going to achieve. So that is why the things are different from the classical computation. So now I will take a pause.
Dr. Bhattacharya, you may take another maybe 10 minutes.
Okay, that is fine.
Yeah. Okay.
So now finally, just winding it up with the quantum gate hardware. So quite obvious, similar to the classical machines, we also have some different gates over here. The gates are actually unitary operators. I'm not going into the details. The unitary operator is that the adjoint is equal to inverse. So different gates are there. Poly-X gate. Poly-X gate similar to the NOT gate in classical computation. What it does actually, if you just start alpha gate 0 plus beta gate 1 state, and then if you apply X gate, poly-X gate on the entire qubit, you will get beta gate 0 plus alpha gate 1. That means the probability amplitudes are being swapped, replaced. So it switches the amplitudes of the states. Similar to X gate, you also have Y gate and Z gate, poly gate. And then finally, the fundamental gate is the Hadamard gate, which actually is creating the superposition. It can create the superposition in the matrix representation given by this. These are all unitary matrices because these are reversible gates. So that means if you just create a superposition like this, for example, if you just apply a Hadamard gate on gate 0, only on Hadamard gate on gate 0, you will get what is referred to as a plus state. And for 1, if you apply Hadamard gate on the gate 1, you will get a minus state. So now, similarly, if you apply a Hadamard gate on the plus state, you will get back gate 0. Similarly, if you apply Hadamard gate on minus state, you will get back gate 1. So these are reversible gates. So entire computation is reversible computation. So now some idea about the different hardware platform architectures. You have the quantum annealer, D-Wave. This is different. The technology is different because they do not use any gates. They use some optimization principles. But the outcome is better than classical, quite obviously. Then you have approximate gate quantum computers, IBM Q, Rigetti, IonQ. Different applications, quantum chemistry, machine learning, etc. You have rely on superposition entanglement. And finally, the target is to have fault-tolerant quantum computers which can deal with errors, noises, and also can be efficient in several specialized problems. And but then you also require a huge number of physical qubits, error-free qubits. So now the different frameworks which are in existence, IBM uses architecture superconducting, platform is Qiskit, the software platform, whatever you tell. Google uses superconducting, platform is CRQ. Microsoft trapped-ion technology, Azure Quantum is the platform. Amazon uses superconducting trapped-ion photonic, and the platform is Bracket. Xanadu uses photonic, platform is Penny Lane and Strawberry Fields. So all of you might have come across these terms. So these are actually being used by different organizations, different companies in their build-up of quantum computer. So what is a qubit physically? Physically, what is a qubit? Something very small, so that you can do some quantum mechanical operations. Depending on the architecture, you can either use photons as qubits or quantum dots or Cooper pair boxes in superconducting architecture. Josephson-Johnson circuits also. Nuclear spins also can be treated as qubits. Single isolated also. Different types of qubits you can have in different types of architectures. Now some examples of different architectures. Photonic quantum computer, you know all these things. Photonic test bed, different components on a test bed. So you can have something circuit like optical quantum circuit also like this. So you can start with some input, ultraviolet pulses or lasers. Then you can use some filters or some polarizing beam splitters. Then you can have this different. Now, what is the principle? Because you can have horizontal polarization and vertical polarization. So these each can be represented as 0, gate 0 and gate 1. So you have two polarizations, horizontal and vertical. You can use it to advantage to encode 2 qubits. Then you can have some different other components, optical components, half-wave plates and all these things to introduce rotation. And then finally, you can also estimate phase. You can finally do some measurement using some detectors. Okay, so you can implement the same thing. Interesting thing is that you do not require very stringent conditions in terms of temperature for this, because you can do it in room temperature. But then you have to maintain the isolation of the environment, because also quite obvious optical test bed should be free from isolation. Free from vibration. So now one snapshot. You can have a photons at qubits, already discussed, horizontal polarization, vertical polarization. You can have the superposed state H plus V, H minus V, plus state and minus state like this. And also you can have intermediate states as well, the diagonal and the anti-diagonal states as well. So Hadamard gate can also be represented like you start with gate 0 and gate 1, you get the plus state and minus state. So by using a halfway plate, you can have these plus state and minus state like this. And also some detection can also be done using polarizing beam splitter in this way fashion. So this can be found in detail in Photonics Quantum Technology new magazine, Nature Photonics. Now the comes to the superconducting quantum. So it is totally based on Josephson tunnel junction. So you have two superconductors separated by serine insulator. So these are Cooper pairs. So the Cooper pairs generally travel from one particular superconductor to another through this thin insulating layer. So if the barrier is very thin, so the phase difference will be dependent on each other. So quite obviously you can get one state over here, another state over here. Now, quite similar to the holes and electrons, the state of a particular superconductor depends on the number of Cooper pairs which is there inside the superconductor. So some Cooper pairs will go on from here to here. So the more the number of superconductors, that will give you one particular state, the less will give you another particular state. So presence and absence of Cooper pairs will give you the particular states, gate 0 and gate 1. So these Cooper pairs actually these charge qubits. Okay. So presence or absence of excess Cooper pairs in the island. So the qubit state is determine the number of Cooper pairs that are tunneled across the junction. So nowadays we are using transmission line Samtec plasma oscillation qubit. It is a specialized superconducting charge qubit, specialized Cooper pair, which have reduced sensitivity to charge noise. So it is one figure from IBM, where have different these are four transmodes over here, and different resonators and readout lines are also over here. So now this is the advancement of IBM technology. You started all over from 2019, 27 qubits. And now 2023, 1121 qubits, Condor, and beyond it is targeted to 1 million qubits, large scale systems. Now quantum annular D-Wave, something different. D-Wave actually came up with a technology based on the stimulated annealing or optimization. So whatever problems you want to solve in a quantum computer of Q-Wave, you have to model the problem as a optimization problem and try to find out the lowest energy level. So something like this, you have to find the coordinates of the minimum value of the energy landscape. If you just look at an energy landscape looking like this, undulating like this, so ups and downs. If you drop a ball, what will happen? It will go to the lowest energy level. Now, interestingly, this may not be the lowest energy level. This may be the local optima, but this is the lowest one. So, in order to move it from here to here, what we need to do is to give a perturbation so that it climbs up the hill and then falls down. So that is done in the case of simultaneous annealing in the classical optimization problem. But then you can just use quantum mechanics to rescue. Now the cost function of this optimization problem can be represented by these longitudinal interactions, longitudinal field, Hamiltonian can be constructed. And if you add a transverse field like this and try to reduce this amplitude of the transverse field in an adiabatic way, very fast from very large value to 0, similar to an annealing process, you can find out the ground state of the system, the state with the lowest energy level. This is actually referred to as quantum tunneling. What is the advantage you are getting in adding a transverse field over here? Something like this, you are getting quantum tunneling. It actually enables you jump from one classical state to another very easily. Wow. So you see, it was the figure like that in the previous case. If you apply the quantum tunneling, annealing, it will directly move from here to here without going from here to here. You did not cross the barrier. So the height of the barrier is not important. The width of the barrier is important. So you can make a tunnel like this and just move the particle to the lowest energy level. So that means whatever problems you want to solve on a D-Wave quantum computer, this is a typical scenario of a D-Wave quantum computer. These are the qubits in loops. These are superposed parts, the junctions. So whatever problems you have to feed that as an optimization problem, as an Hamiltonian, and the qubits will arrange themselves in order to find out the lowest value of the Hamiltonian. So once you get the lowest value, you can just use some readout lines to read the qubits from here, or from here. Okay, so this is a typical snapshot of a D-Wave 5000 qubits machine. So finally, some of the application areas, almost every sphere now is banking on quantum computing, artificial intelligence, better batteries, quantum sensors, weather forecasting, optimization, financial modeling. We are working on these, financial modeling, also working on these, also working on quantum sensors and all these things we are working. Drug development also we are working on this. So there are lots of areas. In fact, all the areas are not taken care of because all those problems which cannot be solved on a classical computer easily in polynomial time can be easily solved by quantum computers. So here are some of the references. And finally, ending up, I thought I would be able to give this idea of this, how to log into quantum IBM Qiskit and visualize. Anyway, you can just refer to this link. You can create an account and can get a flavor of the IBM Qiskit platform where you can play with qubits and also do some programming and solve some problems. So thank you very much for this opportunity. I am now open to any query which you might have.
Dr. Bhattacharya, I am having two questions. You talked about the quantum entanglement, and in the quantum entanglement, you have nicely demonstrated with the Bob and Ellis story. But my question is that when you are making the quantum entanglement, in that case, you are telling that velocity of propagation will be more than the speed of the light. Then actually, how is it happening? Is it not contravening the Einstein proposition?
Yes, actually, the proposition is contravening, but then it seems as if you are having something which is moving beyond the speed of light, because you do not have any formal communication channel, nothing like that. Because even if you want to move something with light, you need a formal communication channel, isn't it? But
Absolutely.
then, as if moving with a speed which is more than the speed of light, breaking the jinx of the highest speed.
Yeah,
it's some sort of visualization I just talked about, but the entire intricacies and details are beyond the scope of the present treatment.
Okay. My second question is that you are utilizing the optical circuit, which you are utilizing optimal quantum circuit, and you are talking about that you are utilizing horizontal and vertical polarization. My question is that can you utilize both horizontal and vertical polarization together, as we are utilizing nowadays in the digital microwave with the cross polarization interference cancellation? You can do it. So can it be implemented here as well, so that you can have the double the throughput?
Yes, also because thank you for this interesting question, because already told you, because if horizontal polarization is going to represent one particular state, vertical polarization is going to represent other polarization state, other state. So you can have both together, because you have the plus state and minus state, both H and F are together. So there is no issue about it.
So are you implementing some kind of, because of the avoiding any error-free communication, because that is the most important thing, and the interference can happen in the cross-polarization border. So do you have any kind of algorithm or solution specific like cross-polarization interference cancellation?
Actually speaking, we are actually working with the Qiskit or superconducting technology. And hopefully, also these things are quite easily implementable, because Xanadu is doing photonic quantum computers. So we can also try to, because some of us have expertise in optical computing and all these things, so we can always think forward. In fact, we had a discussion earlier with Dr. Palodi regarding this, setting up something similar to this, maybe a prototype. So we can always try. There's no point in stopping over there.
Thank you, Dr. Bhattacharya, for that excellent and insightful discussion today. Can we get the slides, please?
Yes, I will mail it to Professor RNC.
Yep. Okay. Thank you.
So thanks, Dr. Bhattacharya. But Shomanjit Gupta, did you have?
May I ask a question?
Yes. I have a simple question. In classical computation, memory is semiconductor based, but here in qubit storing,
you cannot store qubits. Qubits cannot be stored, cannot be copied, cannot be replicated. This is the main disadvantage. What you have to do, one shot. You cannot store anything. How can you store a random probability,
any quasi material?
Sir, can I ask something, sir? Sir, what is D wave? Actually, I just.
Sorry. Just can you hold on, Suman?
Okay.
Please carry on.
Any quasi material is there for storing?
I do not have any that idea, but you can always prove that quantum qubits cannot be stored.
Okay.
Quantum memory is far from being realizable as of now.
Okay.
Sir, my name is Shoykot Majumdar. Actually, I have a question. Actually, you told that photonic quantum circuit. Is there any simulator is available to design any photonic quantum circuit?
Yes, I do not know the simulator, but then you can use that actually Amazon. We try to so the circuits, the algorithms, the platforms are made of this particular circuit. But then simulator with the simulators are there or not, I do not have any idea. So you can ask our professor.
So actually, in IBM Qiskit, I have an account, but in using that account, it is difficult to design photonic quantum circuit.
You cannot design that because these are interfaces to the IBM cloud computing, IBM quantum cloud. So
Yes.
that is behind that you have the superconducting circuit only. You cannot design anything over there. You can have to design it offline, and then you can use some interface, some platform like a bracket and all these things to make your programs and do it.
Thank you.
Okay. Suman, you had a question. And by the way, Suman, you go on mute.
Yeah, sir. My question is very simple. Whatever the hardware we have designed through IBM, Google, Amazon, whatever the hardware we have designed till now, so the power of ability to connect that hardware, I'm talking about the algorithm. So what is the degree of security?
I didn't get you. Can you please repeat?
If we make a hardware, okay,
Yes.
regarding quantum computing, so design the which company is the best? IBM, Google, or Amazon?
It depends on the technology you are going to adopt, whether you are going for superconducting or any other trap.
Yeah, sir, superconducting, sir.
Superconducting, IBM is now the front runner.
Okay, sir. Okay, sir. Thank you, sir.
Any technology to your advantage, depending on your expertise or your interest.
Okay. Thank you. So, Konik Palodi, your question, please.
Yeah, hello, Siddhartha. With your permission, if I may just add that there was a question regarding quantum photonic simulator. Currently, there are two simulators available. One is known as Sequence, the other is known as Picasso, which have very basic capability of photonic qubit simulation, but it is quite difficult to sort of access them, and not only that, to exactly understand and to use them. So with this just anecdote, I will just ask you one simple question regarding quantum state. So when we are doing polarization, essentially we are doing it in classical domain. So but in general, when we talk about photons, we actually meant it in a more sort of a quantum domain, because photon is actually the energy which is released due to jump of any particular from one state to the other. So whether in these sort of cases, whatever setups, or you have mentioned superconducting, then ion trap, in more of these cases, the current hardware, whether they are in the state of hybrid, I mean classical and quantum in between, or we have actually reached the state where we can actually do pure quantum.
No, I told you, pure quantum is far from being reality. You have to have some classical components as well. First of all, you have to, whatever inputs you are giving, it is in classical domain. You have to have some classical interface. And then you can move on by converting, encoding to quantum domain, doing some computation in the quantum domain. And furthermore, at the end, you have to have it in the classical domain as well. So then you have to also require some classical electronics. Moreover, since you can, these are not iterative processes, whatever iterative algorithms, classical algorithms you need to implement, you cannot do that. You have to just take the measurement, intermediate measurement, do some updation in the classical domain, iterative measurement in the classical domain, and then again fit the outcome to the quantum domain. So some variational quantum algorithms are there where the qubits, so the quantum gates are actually variational. That means they can access some parameters which can be varied. Those things are quite in place there, but then you cannot always dispense with the classical. You have to have classical electronics.
Thank you, Siddhartha. Thank you.
Okay. Next question was Ananya Chaudhary, Chakraborty or Ananya Chaudhary.
Yes, sir. So my question is about the entanglement. You said we're using qubits for the quantum computers. So for that we need the entanglement particles. So sir, how come we make those entanglement particles in IBM or whichever, like IBM or Google, they are making some qubits and they are entangled, right? So how are they making those entanglement particles?
Entanglement, it is actually Bell step. So you see, this is a very rudimentary overview. We didn't go into the techniques and the entire physics and all the mathematics, because there's some materials. You can just look at the literature. Very simple. You can use some gates, Hadamard gate followed by NOT gate, CNOT gate to get an entangled pair. No issue. Because the gates are designed in such a way that you can always get an entangled pair. Like for example, if you apply